Alright, so today I want to talk about integration using inverse trig functions. But first, you're going to have to memorize very important equations that you'll need for basically everything you do with this unit. For the first one, I'm going to start out with the arcsine equation. It's going to be dx over the square root of 1 minus x squared, which equals arcsine x plus c. That's the first one. That's the arcsine equation. For the second one, I'm going to do the arc cosine equation. It's going to be the integral of negative dx over the square root of 1 minus x squared equals the arc cosine of x plus c. And then here's the arc tangent equation, which is going to be dx over 1 plus x squared, no square root this time, equals the arc tangent of x plus c. And now that we're finished with the basic trig function, we'll go over to cosecant. So the cosecant equation is going to be the integral of negative dx over absolute value of x times the square root of x squared minus 1, which equals the arc cosecant x plus c. So for the next one, it's going to be the arc secant. It's going to be the integral of dx over the absolute value of x times the square root of x squared minus 1 equals arc secant x plus c. For last but not least, it's going to be arc cotangent. Arc cotangent is going to be negative dx over 1 plus x squared equals the arc cotangent of x plus c.
So, my friend Clayton showed you the 6 different inverse trigonometric function equations. And now we need to do an example. So, for example 1, we're going to have an integral. And it's going to be the integral of 1 over the square root of 1 minus 4t squared dt. So, whenever you look at an integral, you should think of a few things. First is you're going to have to try to picture the inverse trigonometric function equation that looks most similar to the integral. And in this case, it happens to be the integral of dx over the square root of 1 minus x squared, which, if you remember, equals the inverse sine. And so now that you know which equation it matches up with, you're going to want to start doing the integral. But to do that, you're going to need to make this equation look like this equation. So what I'm going to need to do is I'm going to need to rewrite it a little bit. Do 1 over the square root of 1 minus, and instead of 4t squared, I'm going to go ahead and make it 2t squared. Because if you square 2t, you're going to get 4t squared. And now it looks a lot more like this original equation, which allows us to solve it. So to solve it, you're going to need to do u substitution. And in this example, our u is going to equal 2t, our du is going to equal 2 dt. Then you divide out of 2, so you get 1/2 du equals dt. So now you're going to have to put the 1/2 in front of the integral, and then rewrite the equation as 1 over the square root of 1 minus u squared du. So, now that you wrote down the new equation, you can recognize that 1 over the square root of 1 minus u squared happens to be the equation for arcsine. So now you can rewrite it as 1/2 arcsine of u plus c. And at this step, you're almost done, but you're not done yet. What you need to do now is put the u back in. So it's going to be 1/2 arc sine of u. Oh, actually, instead of u, you're going to write 2t plus c. And that is your final answer.
Alright, so for the second example, we're going to do a definite integral this time instead of an indefinite integral. So we're going to take the definite integral of sine of x over 1 plus cosine squared of x from 0 to pi squared. So, or pi halves, my bad. So right off the bat, looking at this equation, I noticed that it looks a lot like the arctangent equation right here. It has a lot of similarities, just in a different form. So first, what we're going to do is we're going to rewrite the equation so that we can do u substitution. And we're going to make it look like this equation as much as possible right now. So the cosine x will be our u. So our u, since it is cosine x, and then I'll make our du negative sine x dx. But we don't want the sign to be negative, so we'll just make the other side negative, and that'll make this the sign positive. And then after we do that, we're gonna want to change the limits of integration. So what we're gonna do is we're gonna plug in the 0 and pi halves in for the x of this equation. So the cosine of pi halves is equal to 0, and then the cosine of 0 is equal to 1. So that'll be our new limits of integration from 1 to 0. And then since we have a negative out front right here, we're going to want to put a negative out front of the integral. And then we're going to rewrite it as 1 over 1 plus u squared du. Alright, and now that we have it looking closer to the normal arctangent equation, then we'll rewrite it, and we'll change the we'll make sure this negative isn't there anymore. And since the negative is there, and to change it back to positive, we'll have to switch the limits of integration. We'll have to flip them over, and that's going to be 1 over 1 plus u squared du. And then you notice that now that this negative is gone, this actually equals the arctangent equation. And then now all we have to do is plug in the limits of integration for u. So we're going to do the top one minus the bottom one. And then the arctangent of 1 is going to equal pi fourths. And then the arctangent of 0 is just going to be 0, so our final answer comes out to just be pi fourths.